Hello, welcome back to Organic Chemistry. Today we'll be talking about enolates. Everything you want to know about enolates, but are afraid to ask. Have you noticed in our previous videos, we worked with a lot of enolates, but our enolates were always symmetrical. Or we always worked with carbonyls that only had one alpha carbon to generate those enolates. What happens if we have a carbonyl that has two different alpha carbon to work with? So let's look at that. Let's look at this example here. How many different alpha carbons do I have on this ketone? I have one here, and I have one over here as well, right? I'm going to have two alpha carbons to work with here. So what happens? How many different types of enolates can we form? Well, since we have two different types of alpha carbons, there are two different types of enolates we can form. So let's look at those. So I can take my base, pull off this proton, and we can generate this enolate here. Or what? I can take that same ketone and let's tack that other alpha carbon over here. Let's use our base. To generate our other enolate. So we have some questions we need to talk about now, right? Which enolate do you think is going to be more stable? Which one's going to be more stable? Is it going to be with the double bond on this side, on the right side, or the one on the left side? What do you think is going to be the more stable enolate? Right? How can we tell the difference? Well, the oxygens are the same, both negatively charged. But look at where our pi bond is. We have a pi bond here, a pi bond over here. This pi bond is going to be more substituted than this pi bond, right? This is our more substituted pi bond. And we've talked about that already. Alkenes. We've talked about alkenes. The more substituted the alkene is, the more stable it's going to be, right? Because of these alkyl groups can help donate electron density to help stabilize that alkene. Same thing we see with our enolates. We have more groups around it, it's going to make that more stable. This is going to be our more stable enolate. Now, even though it's our more stable enolate, they're both going to be reactive. They're both going to make an enolate here. It's going to react with other things, right? So that's our more stable enolate. Now, what's another name we can call our more stable enolate? What's another word for it? It's also known as our thermodynamic enolate. Thermodynamic enolate. Okay, that's going to be our thermodynamic enolate. Now, if this is going to be our more substituted, our more stable, or our thermodynamic enolate, this is going to be what then? This is going to be our kinetic enolate. Okay, so we have our thermodynamic enolate, which is formed on our more substituted side. Then we have a kinetic one on the least substitute side, right? Also, there's some other information we know about this, right? Our thermodynamic one, we have to pull the proton off from the more substituted side, right? This is going to be a lot slower, right? It's going to be a lot slower to form that enolate. Where this one, the kinetic one, we're going to form this one a lot faster. This is going to be our faster enolate. This is going to be our slower enolate. Okay. When we talk about slower or faster, it's basically this idea that how fast can we make this enolate? We can make this enolate very quickly because this is not very hindered at all. So we can pull off the proton very easily and go right into the kinetic enolate. For thermodynamic, it's a little bit slower, right? Relative to each other, this one's going to be a little bit slower to form. But we're forming that more substituted enolate, which gives us that more substituted, more stable enolate. All right, so we have two different enolates. We have thermodynamic, we have our kinetic. Now, this is pretty interesting because our kinetic enolate means that we're going to have this carbon here work as our nucleophile. Our thermodynamic one, this carbon here is going to work as our nucleophile. So we can add groups at different places. So that's pretty useful, right? Now, our only problem is how are we going to form the kinetic one versus forming the thermodynamic one? Let's start with the kinetic one. We want to find a way to make this very quickly. We want a very, very strong base that's going to pull up that proton very quickly, generate the kinetic one, and we're in business. So what kind of base can we use that would give us this enolate very, very quickly? So let's talk about the kinetic one first, and then we'll talk a little bit about the thermodynamic one. So as I erase the board, we can start thinking about what base do we want to use that's going to be a very, very strong base that we can deprotonate things very, very quickly to give us that kinetic enolate. Any ideas? Is there a strong base we've used recently? Very, very strong base? We mentioned it once already. So let's start over here. So we have something like this. We're going to use our very, very strong base. And remember what it looked like? This is our strong base. This was what? This was going to be our LDA. So we use our LDA base. Now, not only are we use LDA, but we're going to do this at very low temperature, minus 78 degrees Celsius. As we talked about, we're making the kinetic enolate. This enolate forms very, very quickly. It forms so fast, we have to worry about it that it forms so fast, it may equilibrate to a more stable enolate. So we have to make it very fast, and we do it at lower temperature so that once it forms, it's kind of stuck in that form, right? It's so low temperature, it's not going to equilibrate into the more thermodynamic form. We're just going to form it real fast, and then it's just going to sit there because it's at such low temperature. Because remember, we talked about this already. This isn't the most stable form, right? And so we formed our kinetic. Now, this is our kinetic enolate, which means that when it's time to work as our nucleophile, what's going to happen? Electrons are going to come down. This means here that this carbon here is going to be our nucleophilic carbon. Okay, this is going to be our nucleophilic carbon. This is going to do then we introduce our alkyl halide, and then it's going to attack, our nucleophile here is going to attack the alkyl halide. And we'll talk about that in the next video. Today, we just want to focus on generate our kinetic enolate and then our thermodynamic enolate. All right, so we're going to use LDA minus 78 to generate that least substituted side, to make that least substituted enolate. So this is going to be our nucleophile. This is going to be our enolate that's going to attack our alkyl halides. Okay, and we'll talk about that. So that's our kinetic one. We're going to do this at minus 78 degrees. Now, for our other one, remember our other one, our thermodynamic one, that's the slow enolate. It takes a while to form, it takes a little bit slower. So we don't want to do it at minus 78 because it's too slow. We need a little bit of heat in there to make sure we get the reaction to move, right? To get the reaction to go forward, to make that more substituted, thermodynamically stable enolate. So for that one, what we're going to do, we use a slightly different base. We'll still use a strong base, but we'll use a base not as strong as our LDA. We'll use something else. We'll use, how about NaH? And we'll do this at 25 degrees. All right? So we're not at so low of a temperature. We're just at basically that room temperature, maybe a little more warmer than room temperature, so that we can make sure we form that more substituted enolate. And we know with sodium hydride, it's a negatively charged on hydrogen, pull that electron off. We're going to form this side here. Oops. And we form that enolate there, right? That's what we're going to form. Now, so, and by doing this here, using our thermodynamic conditions, again, at warmer temperature, we're going to go, it's going to go a little bit slower. We're going to pull off to form the more substituted enolate there, okay? Form our thermodynamic enolate. Right? We form our thermodynamic enolate. Remember, we want to do this so that we form this more substituted form. This would be the more stable form. Our kinetic one, we want that to go really fast. We're at low temperature, so we can form this one, and it's kind of frozen in this kinetic enolate, so that this can then go and attack our alkyl halides, right? Our electrophiles. So same thing with this one. This is we're gonna have our resonance. Make sure we're clear on this. This carbon there, that's our nucleophile. Okay. This carbon here is going to be our nucleophile that's going to then attack our electrophiles. Generally, going to be alkyl halides. And we'll look at that in the next video. So now we have two ways. We can form a thermodynamic enolate, which can then we can attack using our more substituted carbon, or we make a kinetic one, which will make our enolate on the less substituted side, and we make this carbon here will be our nucleophilic carbon on the least substituted side. Right? So now we have a way to add carbons to either side of our ketone, whether it be the more substituted side over here or the least substituted side. Now in the next video here, we'll use these and put these into practice, right? We have some conditions now. Let's see if we can start building some molecules with that.